now let's talk about our second type of question. Here, instead of just like dissolving our acid in water, we're actually going to be mixing it with a base. And so we're going to have our acid reacting with the base and leaving us with the conjugate base of the first of the acid and then the conjugate acid of the base. And we can be asked the same sorts of questions about the concentrations of our acid and our base. But in this case, things are more complicated because we have two that we need to consider. So we have two sets of acid and bases. And then we could be asked the pH of the solution again. And here we have to take into account that we have both those things going on in the solution. So let's go ahead and write out, sketch this out. In this situation, what we're going to have is we're going to have our acid, instead of just writing HA and A-, because now it's going to get complicated because we have two of them, I'm just going to be writing, start by thinking of just one as the acid and one as the base. Now, these are going to react with one another. And again, you're going to reach an equilibrium. And this is going to reach an equilibrium where you're going to have your conjugate acid plus your conjugate base. So remember that this acid is going to contribute to this conjugate base. And this base, well, this is going to be its conjugate acid. But they're going to be reacting with one another so that for each amount of the acid that you lose, you're also going to be losing that amount of the base because these are going to be reacting together. And that's going to leave you with that amount of the conjugate acid and that amount of the conjugate base. Now, in one of these situations, what we're going to be dealing with in this simplest case is that you're starting from zero. You're starting from zero of the conjugate acid and the conjugate base, and you're given how much of the initial acid and base that you're going to have. So what we could do is we could write out our ICE table again. Remember, that's the initial, the change, and the equilibrium. So here our initial concentrations, we're going to be given the amount of the acid, we're going to be given the amount of the base, and then the conjugate, we're going to have zero of each of these. So our change in acid, this is going to be our minus X, our minus X. Then we have a plus X and plus X. And then at equilibrium, we're going to be left with our given minus X and our given minus X and our plus X and our plus X. Now remember that if we have something that is at equilibrium, we can write an equilibrium equation. We can write a KEQ equation. And more specifically, if we have something that is an acid reaction, an acid dissociation reaction, well, then we can write a Ka equation. But in this case, we're going to have the Ka of both our acid and we're going to have the two Kas. So we're going to have two pKas for the individual acid and base reactions that are going on in here. And then we're going to have an overall, Ka for the equation. We're going to have an overall KEQ for the equation. And no matter what type of equation that we have, the same thing holds for a KEQ equation. It's going to be our products over our reactants. No matter what type of equation that we're dealing with, it doesn't even have to be an acid dissociation reaction, any type of equilibrium reaction. And so in this case, what it's going to be equal to is our KEQ. It's going to be equal to our products. So we have the X from our conjugate acid times the X from our conjugate base over our reactants. And so we're going to have our given acid concentration minus X times our given base concentration minus X. And this is going to be our KEQ equation. Now, where do our pKas come into account? We can't just use that pKa and plug it right into this KEQ because we have those two pKas to worry about. We have the pKa for each of the acids. So remember that when we're dealing with a pKa, so pKa is always for an acid. So even if we're talking in terms of a base, we can talk about its pKa in terms of its conjugate acid. So what we're going to want to do is we're going to want to use the pKa's for this acid and for this conjugate acid. So this is going to take into account the strength of our base by taking into account the strength of its conjugate acid. And then we're going to have the initial acid. And so that's the one we've been used to dealing with the pKa for. Now, in order to combine them for this equation, we're going to use that shortcut that I mentioned earlier. And so you can go ahead and figure out how it mathematically works out. But it simplifies down to KEQ equals 10 times the pKa of your products minus the pKa of your reactants. And so when we're dealing with the products, well, that's going to be your pKa of the conjugate of the conjugate acid. And then your reactants, that's going to be your pKa of your acid, like your initial acid. And so now that we have this equation, we can go ahead and we can rewrite this and we can say, okay, well, we have our 10 to the, and so we have 10 to the pKa of your conjugate acid minus pKa of your acid equals x squared over your given, let me just copy and paste that because I am not very good with writing on this thing. And so I already wrote it once badly, so why not just use it again, badly written. Okay, so it'll be like that, except we can simplify this x times x, we'll just say x squared. And now we have an equation that we can go ahead and we can solve. And so let's go ahead and use this equation with an actual example. And if you wanted to, what you could do is you could write this ice table with your actual values in the example. But I'm just going to simplify things and I'm going to jump ahead and use this formula that we just calculated. And we're going to use this in this following example. The question is, what is the pH of the solution formed when 150 millimolar acetic acid, so that's what we were just dealing with. But now instead of dissolving it in water, what we're doing is we're mixing it with 50 millimolar ammonia. And the question is, how much acetate is formed and how much ammonium ion is formed. So let's go ahead and sketch out what equation we actually have going on, the reaction that we have going on here. We have that same acetic acid, and it's going to now be added to NH3. So this is our ammonium ion. And now what's going to happen is our ammonium ion is going to go and it's going to grab onto that proton, and what we're going to get is we're going to get an equilibrium reaction where we're going to have our acetate plus our ammonium ion. So this is going to be our ammonia, and this is going to be our base, and this is going to be our ammonium ion, and this is going to be the conjugate acid of that base. And then this is going to be our acetic acid, which is going to be our acid, and our acetate, which is going to be our conjugate base. And so now let's think about the numbers that we're going to need. We're going to need the concentrations of our acid and of our base. And so we're given that, so we'll just deal with that when we're with the given numbers. We're also going to need the pKa's of the conjugate acid and the acid. Okay, so the pKa of the acid. We're going to want the pKa of the acetic acid, which we had before and we have again, which is going to be 4.8. Now, we're given two pKa's for the two other pKa's. We're given the pKa of ammonia, and we're given the pKa of ammonium ion. Let's think about what the pKa for ammonia represents. So this is our ammonia. And so ammonia, yes, it can deprotonate. It has 3 protons. It can give 1 up, but it has a pKa of 37. It's very, very unlikely to give this up. What about ammonium? This is going to have a pKa of 9.3. So that is a more reasonable, that's a more reasonable thing. And this is actually going to be the one that we want because we want the conjugate acid. We don't want the pKa of ammonia because that's telling us about ammonia deprotonation when we want to know about ammonium deprotonation because our ammonia is going to be the base in this case. So what we're going to want to do is we're going to want to use this ammonium ion pKa, which is going to be 9.3. Okay, so now what we're going to do is we're just going to plug and chug. So we have 10 times the pKa of our conjugate acid, which is going to be that 9.3, minus the pKa of our acid, which is 4.8. And that's going to be equal to x squared divided by our given acid minus x. So that would be our 0.150 minus x times our given base minus x. So that would be our 0.050 minus x. Simplifies down to 10 to the 4.5 equals x squared over 0.150 minus x times 0.050 minus x. And now I'm going to go ahead and I'm going to plug this into Wolfram alpha. So once again, it's going to give me two answers. So x is either equal to 0.0500 or x is equal to 0.1500. So now let's think about which of these is actually right. It's not as easy as before because one of these isn't negative, but we can still figure out which one is correct by thinking about what is our limiting reagent. What do we have more of? Do we have more of the acetic acid or more of the ammonia? We have more of the acetic acid. So our limiting reagent is going to be the ammonia. And we start with 50 millimolars, which is 0.05 molar. Now, if we look at one of these answers, 0.150, that is going to be, basically, that is going to be more than the amount of ammonia that we started with. This is, if we had 0.150 as our x, remember that that's our x is going to be equal to this ammonium ion concentration. And this would be saying that even though we only put 0.05 moles in there, well, somehow we magically ended up with 0.150 moles of it, the protonated version of it, which is not possible. So instead, we can ignore this bigger solution, and this 0.0500 is going to be our answer. And note that it's not like exactly 0.0050, and depending on what you're rounding, you're going to get a slightly different answer. But basically, most of it is going to be reacted, but you're not going to have more reacted than you would have going in. And so this 0.050 is not just our ammonium ion concentration, but it's also the concentration of our acetate. Because remember when we had our ice table, X was equal to both the concentration of that conjugate acid and the conjugate base because the acid and the base were reacting together. And then we can go ahead and we also need to remember our units. So this is going to be molar.